talk about something other than just existence and uniqueness. Otherwise, you get the impression that SPDE and only studies well posedness. Of course, that's the main problem. But the next thing is, of course, to study path behavior or also behavior of distributions when we, for instance, study invariant measures, asymptotic properties like existence of random attractors. So there is a whole machinery that is being developed for that. And so this is, of course, a very special type of asymptotic behavior, namely that the solution simply dies at a certain point and is gone for certain classes of equations. And this is type of porous media equations, namely these so-called fast diffusion equations, and also even more singular cases which are related to models in physics which describe the phenomenon of self-organized criticality. Okay, so let me first give a short overview. So the first part of the talk will be about these extinction results. In finite time, the process is long. And in the second part, so that is for porous media type equations, including the fast diffusion equations, and even more singular equations. So the function psi, if you remember the porous media equation, is even a Heaviside function. So it's this type of equations. T is equal to the Laplacian of some function psi of x of t dt plus a noise. And the noise in this talk will always be, roughly speaking, this one. So this is not well defined. I have to take convergent, so I have to write this as a series and put convergence factors inside, but I just write this a little bit more rigorously like this. This function psi can even be a Heaviside function, so very, very singular. In the fast diffusion case, it's like a square root, and I will explain this in a moment in detail. Okay, so the letter, as I said, described certain continuum models for the phenomenon of self-organized criticality. This distinction results have been obtained over the past roughly 2 to 3 years, but recently we have made an improvement, more precisely last autumn, and I'm going to talk a little bit about these improvements. In the self-organized criticality case was only shown, extinction was only shown when the underlying domain is one-dimensional, so that we cannot do higher dimensions. Now we have progress in this. In particular, one problem I'm going to talk about is at least that we can prove in all dimension asymptotic extinction. Yeah? So this is in the second part here. So the second part of the talk is that we cannot prove it dies in finite time, but at least asymptotically it dies. With probability 1 even, not just for positive probability. This is another deficiency for our extinction results, that for instance psi is the Heaviside function. We can only prove it gets extinct with positive probability, but for other singular psi's, meanwhile we can prove it's really extinct with probability 1, but I will tell you about this. And for the asymptotic extinction result, there is a new technique that we developed since 1 year, roughly speaking, is to transform the stochastic PDE, because it's linear multiplicative noise. So we use a standard transformation from finite dimensions, which we proved an infinite dimensional version of that. And this transformation then makes this equation, transforms this equation into a deterministic nonlinear PDE with random coefficients, so the coefficient dependent on omega. This new PDE that comes out we call a random scale stochastic porous media equation. And using this equation we were able to prove this asymptotic extinction in all dimensions. And I try to give you an overview of the results and also show you the main trick in the proof, how to apply Ito's formula to get extinction results. And of course extinction results for deterministic PDE, or even ordinary differential equation are well known, but in the stochastic case they could not be adapted right away because there is always the martingale part, and you have to take at some stage expectation, and then these classical methods they could not deal with this expectation, because you would have to use Jensen's inequality in the wrong direction. So this, for several years, got us completely stuck on this question. But using this transformation, for instance, or now, and I will not provide the transformation for the extinction result, but we found another method what you should use in the case of stochastic equation. So here's the papers that basically are related to this, and I'm very sorry, I have to apologize, I forgot to update the references. So, for instance, this one has appeared, so this is about this random porous media equation, has appeared in Journal of Differential Equations, and also this asymptotic extinction rate has also meanwhile appeared in Communication Math Physics. And this kind of survey paper appeared already early this year in Journal of Mathematical Analysis and Applications. So just in case you would like to check these papers, but they're all on archive and so available. Okay, so let me first motivate the thing a bit from the physics point of view, namely about these models of self-organized criticality. So you can find this is quite a good paper, also readable, I think, for mathematicians. This phenomenon of self-organized criticality, the most famous one is the avalanche dynamics, or like the sand pile models. You pour sand on a pile, and after a while there is an avalanche, and then you pour again sand and sand, and there's an avalanche. And it's the same, for instance, when there's snow, it snows and snows, there's an avalanche, and so on. And so the idea is that somehow this system, I mean, this avalanche thing is, physicists say, well, it depends on which physicist you talk to, but say that this is the sort of the critical phase, so it goes into an avalanche. And then there is input of energy, and it goes again into an avalanche. And we take a very, so this is modeled normally in a discrete way, but these guys, Banta and Giannoli, they said, well, we should model this in a continuum situation, and what comes out then is a nonlinear differential equation, which is exactly of porous media type. And the input of energy, so for instance, you couldn't interpret this snowing or this pouring of sand, they think of a random energy input, and they add a random part. Yeah? And then the question was, well, do you have this sort of critical self-organized criticality behavior, and we model this avalanche as going to zero and get stuck in zero. So we do not do this periodic dynamics, but just does it go to zero? That's the first question you have to solve in this approach of Banta and Yambos. And we are going to, and this is exactly what we solve this problem, but only in one dimension. Okay, so this postponed the phenomena in the case of the avalanche by a singular diffusion equation. And these are the two basic papers. Now that's the Bach-Time-Wiesenfeld model. I will tell you about how it looks in the continuum interpretation using a nonlinear PDE. And there's also the Zhang model. So this is a little bit different. And meanwhile, we have solved the Zhang model in all dimensions with probability 1. For the BTW model, we still don't know. Okay, so now physicists normally don't write xt, so xt in the porous media equation is also density, depending on time at the spatial point psi, let's see an open set in RD. Physicists, they call this rho for density. Yeah? So I have to, later on I change back to normal notation, but here I use physicist notation. Okay, and then you have such an equation. So they, Banta and Giannoli, by some arguments, some scaling, I mean, they have this dynamics first on 2 time scales. Maybe there's this avalanche, and there's pouring in the snow. And then they take a limit, the 2 time scale becomes closed, and then they can derive this equation. I cannot say that I rigorously understand this kind of derivation, but at least I believe at the end that it's an interesting equation. And they pose the problem, can you prove extinction, and we can prove it. And they actually assumed that, well, you should add additive noise here, and then you should still have extinction. They proposed this because this is impossible, because the noise would definitely destroy this, but with linear, you can imagine if this is zero, there's no noise, so then if it's extended, it stays extinct. So therefore we did basically the thing for linear particle category. So what is this psi in these self-organized criticalities is really very singular, so it's a function which is rho c, there's a critical case which we put later on equal to 0 just by shifting, and so they look at such kind of a function. So there is just the Heaviside function in the one case, which is the difficult, the Bach-Time-Wiesenfeld model, and the Zhang model is f of rho is a linear function, so it looks like this. Okay, so now you have some critical value, rho c, and then so one is this model for the function psi, this, and the other one is this one. Okay, that's the other model, the Zhang model. So it looks like this. And I will do, well, here still rho c, but it's not important. I will just shift everything into 0, because, so I will look, the rest of the talk, I just take this to the c. Just look at this. So this would be the function, the rho times Heaviside function. Let's call it psi. So these are the functions psi. This one is the Zhang model. The other one is the BTW model. Okay, so now why should the solution get extinct? So why should it die out? And it's a very simple informal calculation. So you calculate simply the Laplacian, so that's gradient, divergence gradient. So you first calculate the gradient formally. So as a psi prime, gradient rho. Then you use the product rule, so you come up with the second derivative, and then go out rho square, and then psi prime Laplacian. Since the psi is increasing, psi prime is positive. Yeah? So there's still diffusion type part, and then there is a drift, this drift. Now, if you think of an approximation, let's say, of the Heaviside function, you can think of taking an arcus tangens approximation of this guy. Then you see to the right of 0, it is concave. So this physicist simply, this must be negative, because it's concave. Okay? And densities are positive, so we're only talking about the positive part. Yeah? So really it's concave, so this is negative. So that means the more concave this function is, and the Heaviside function is the most concave one you can think of, the more chance you have to have extinction, because then this becomes very, very big. And this is like a drift with a minus sign that pushes you back into 0. So that's the interpretation. So you would expect this, there's extinction. And this was not even proved in the in the deterministic case at all. There have been papers at the beginning a few years ago about numerical analysis and numerical computations, and these simulations suggested there should actually be extinction. So. And if you add a noise, then people were not clear about it. Will there be extinction or not? And so far, we can, as I said, we can only prove in the really difficult model, we can only prove extinction with positive probability. Okay, so then we were introduced to this problem by my colleague, physicist friend Philippe Blanchard, and then we started to work on this, and so this comes out. So first of all, I would like to, of course, point out that this is purely informally what I calculate here, because psi, I mean, is very, very at 0, so it's not even a measure. The derivative becomes a distribution. So look at just how singular all these things are. Yeah, but if you think in terms of an approximation, you can sort of understand that they have the right intuition. So that's the self-organized criticality case. Now this is the fast diffusion equation. You see that the psi now is given by some power alpha, where alpha is less than 1, so somewhere it's here. So that is what is called the fast diffusion equation. If alpha is bigger than 1, remember this was in my scaling was the p bigger than 2, if you remember. I stressed that in the main lecture, the p is greater than 2. So this exactly corresponds now to this space, because I put alpha there with the sine function here, and then before I wrote this minus alpha and times 1. That's the same as putting the sine function. So this case we already know. That's the classical porous media equation, and you cannot expect extinction there, because the function psi is like this. So it's not concave to the right. You would not expect any extinction. Nevertheless, is a singular. It is called a non-degenerate case, because if you look at this psi at this guy in front of it. Laplacian, it will have a 0 if you have some polynomial there of some order at 0. So that is, there's no, it's not predictive. Anyway, so this is called the degenerate case, and this is the singular case if alpha is less than 0, 1. It's just names for the fast diffusion case. Okay, so as I said before, as alpha is equal to 1, this is just the heat equation. Alpha bigger than 1, we discussed in the lectures yesterday. So as alpha is equal to 2, equal to 0, then this is updating a function, just the Heaviside function, right? Because just a sine function, Heaviside function, shifted up and down is more or less the same, right? So that means alpha equal to 0 is the one that is what is so-called the self-organized criticality case, and now the other one is the fast diffusion case. Okay. So, but in contrast to the self-organized criticality, has been known for a long time in the deterministic case that we have extinction for this kind of equation. The fast diffusion equation has been studied, look into Vasquez's book and you can find all the results, and classical results, but not in the stochastic case. And what we have done is we have also proved extinction, in this case when alpha is not 0, also in the stochastic case. But again, only with positive probability. So also there, it is open whether this is probability. Okay, and I would like to explain the techniques how to prove such things. Okay, so now let us fix our notation. So omega is now a bounded domain in RD, with smooth boundary. And now we switch notations. So for the physicist, the initial density for which you start the equation, they call it rho 0 of psi, we call it x of psi, so x is now a function of psi, and so it is the initial condition, so time independent. And then the solution of the equation, I denote as usual at x here. Psi is the spatial variable. So that's a change of notation. Then I write as usual the deterministic equation in its increments here, so in Monty integral form, and so I replace the row, so now we are really back to our old notation, and now I add the noise. Okay, so now everything becomes depending on omega, meant in integral form. Okay, but now the problem is such a psi here is at this point multi-valued. And you can say it's not multi-valued, just makes a jump. But analytically, it's better to treat such a function psi as a multi-valued function where you just fill the gap, and you say at point 0, the value is a set, so it's a multi-valued set. So that means, really, if I now apply a multi-valued function to another function, then this becomes again a multi-valued function. This is multi-valued, so, but this is single-valued, so really I should write it like this. It's contained. Yeah? So this increment, which is really fixed function, is contained in this set of function, because that is multi-valued, it becomes a set of function. This is just a way to write it. Yeah? I will tell you exactly what I mean by a solution, and then everything becomes clear. Okay, so this, now we are back to our own notation, and now we can talk about conditions. Yeah? So that is the appropriate SPDE, as I just told you. Now I have to recall the boundary condition. I take the Laplacian with directly boundary condition, so I have to make sure that this is really 0 on the boundary, but now this is set valued if the psi is multi-valued, so I have to write that psi of x is equal to 0 on the boundary, but the 0 is contained in the image of the psi of x. So that's the way how to write informally that we are working with directly boundary condition, and that is just our initial condition. Okay, so now we are looking for a solution to this equation. This will describe the density of a substance in a porous media in the classical case, and now it will describe, this sort of simplified self-organized criticality behavior. Okay, that's the initial data. So now the noise, now I'm more precise. You see, I really multiply x by the Brownian motion, but I do it in such a way that this becomes a Hubel-Schmidt operator. So I introduce converging coefficients here, so I will give the definition on the mu k in a moment. So that should be square sum of them, basically. Now this is the noise. That's just the usual noise that we've seen all the time, but just written in coordinates with respect to the orthonormal basis of the Laplacian. So I take the orthonormal basis of the Dirichlet Laplacian, so then I write the noise this way. So now I have to explain what is this multi-valued function. You see, psi is a function from R to R, but it really takes values in the subsets of R, because here it is single value, but here it is multi-valued. So it's a subset valued function. So that is also called, of course, a graph. It's a graph. It's a subset. It's a subset of the product space of R itself. Now I have to tell you what is a monotone graph. A monotone graph is a subset of R cross R. If you go to the right, you always have to go up. Can you imagine? So like here, you go to the right. No, I don't go up, but I also do not go down. Yeah? And then I go up. And also from any point here, if I go to the right, I have to go up. So for instance, if this was a strip, it would not be monotone, because on this middle piece you can go down. into the next step. So it always have to go up. That's monotone. And maximum monotone means if you have a point and you enlarge the image set, yeah, then you destroy the monotonicity. Then it's maximum. You cannot make the graph bigger, keeping its monotonicity property. Yeah, then it's called maximum. So this is definitely maximum monotone, right? Because you cannot never make it bigger because then you can go down. It's no longer monotone. So that is an example of a maximum monotone graph. But you have lots of jumps like this, but you have to have just jumps. No? Because if the jumps has a width, then it doesn't work because you can go down to the right. You find one value in the value set, which will go down. So I hope this gives you roughly an idea of this approximation. But always think of this example. I will make this example a little bit more general in a second. Okay. So now here's the condition what I assume about this non-linearity psi. So now I write the Heaviside function as a sine function. Yeah, the sine function now really as a multi-value function times some height here, and then I add another function. So now let's write. Now draw the picture. What is the general situation? We can be done even more general, but that's not so important. So you should always have this picture in mind. What is the psi? So the psi has a jump here, maybe not symmetric with respect to 0, and right. So there is a height. So this is the height of the jump. Okay, that's the height of the jump. So this was the sine function, but the sine function I push up and down by some other function. It doesn't have to be linear, but you should nevertheless have this picture in mind. It looks like this. But it can also be flat. It doesn't have to be like this. What is before 0 doesn't interest us anyway, but just for reasons of proofs, I mean, we have to have something on the left, and in order to then we prove, if we start with a positive initial condition, it stays positive. And then we don't have to worry about it. So that's the kind of function psi that we have in mind. There can also be some other Lipschitz function that you have as long as it's Lipschitz. So you see psi tilde, what I have is Lipschitz, and C1 outside 0. And the other thing you should avoid when you shift the sine function up and down, and I should stress it's multi-valued, so at 0 it's this whole interval. So if you shift the sine function up and down, you should not shift it below 0. Yeah, so therefore I have to make this condition. What I shift at 0 should not put it below. Yeah, so it must have a little bit upstairs. And the same we can do basically for the fast diffusion case. So here the alpha, there basically alpha is 0. Here is alpha between 0 and 1. And we work only dimensions 1, 2, 3, the physical dimensions. And then we can prove extinction as in the deterministic case, in the fast diffusion case, only if the alpha is at least 1 over 5. Yeah, so that is just a restriction comes from Sobolev embedding. Whether it's generic, I have no idea. Okay, so that's the condition on the psi, and on the next page I give a concrete example. So such a psi, and that's exactly this kind of psi. Yeah? You should always think of such a psi. This is the analytic way of expressing such functions. And here's the definition, here's the condition on the convergent factors that I put into the noise. So that is a good condition, that is strong enough, let's say. It's not the weakest possible. So even multiplying with the eigenvalues of the Laplacian, which are very big, they should be finite, then everything goes. Yeah? It is not the most general condition. So the dimensions 1, 2, 3, you can write it this way. Okay, so it can also be 0. No? The deterministic case is always inside. So that was the example. Now, the question, I already told you that in the porous media case, you work with the Gelfand triple, V star V, where the V, so we will not so much work with this triple. I will use a little bit different approach here, but this is just the space H minus 1, which is the dual space of the directly Sobolev space over our domain. And with this in a product, which I already did. So this is informally written, but I think it's intuitively the right way to put it. And then I have to define what is this operator as before. And the point is that you now X is a function. You apply this to a function. This is maybe multi-valued. Then you apply the Laplacian. What do you mean by that? Well, I can do this by just defining the domain. So the domain is all X in L1 intersected with H. Okay. Now you apply psi of x, which is composing with a multi-valued function, so that's a set of functions. Yeah? And the domain is if you can find a section in this set of functions, yeah? So which is in H1, and then you apply to this guy the Laplacian in the usual way, to all of them. Yeah? What does it mean, all? So eta is now a function of psi, let's call the object in psi, so you have to make it better to more intuitively to understand, you do the following. So eta at point psi, that's now a real number. Yeah? This is to be true for almost every psi in the underlying domain. So that's contained in psi applied, so these are all x, applied to x. Now this is a set of real numbers at every point psi. Now this is a function, you apply psi, this is multi-valued, you do that at every fixed point psi. So you get a set of real numbers here on the right hand side for every given psi. And this is exactly what you want. You want this, so if you think of this as a multi-valued map, you take a section in this map which is single-valued and has the right regularity properties. The Laplacian goes from h plus 1 to h minus 1. So that's the definition, and then I can prove, you can find this in the book of my course, Bamboo, so I didn't mention most of the work is together with Viorella and with Giuseppe D'Aprato, and also with Stanley One. So you can find this book, and then you can find that this is a maximal monotone operator on H, but all these things I don't really need in this talk so much. Okay, so now I give you a definition of a solution which deviates from the general theory that I presented yesterday. I rather now prefer to write down analytically weak solutions as Professor Krylov and also Professor George did in this lecture, mainly. So now I define this as a solution. So an H-value process, H again being minus 1, this continuous FT adaptive process is called a solution of our SPDE. This was this multi-valued guy, this animal, looks like an animal at the first sight. And so that it weakly solves our equation. Now let us have a look why it's really a weak solution. You take xt on the left, you take inner product with the test function. It's enough to take simply the eigenvectors of the Laplacian as test function because the span of them is dense. Yeah? So you test with sufficiently many functions, and it's linear here, so you test the equation with respect to the set of test functions. So you test the process. Okay, if you want, this is not L2, this is the L2 and I put here, but this is in H minus 1 and Hj is in H plus 1, so that means this dualization is always well defined. And then you take the initial condition, comma the test function, and then you take the noise, here's the noise written in coordinates over k, and you take inner product with the test function Ej, and just take it in the stochastic interval. So it looks like this, yeah? Just by our noise. And then let us look at the drift term. So this I've just integrated by parts, so the Laplacian should be really on the other side. It should be here, Laplacian of this, of eta. But what is Laplacian of eta? Laplace of eta is simply Laplace of psi of x by our definition. So we really solve this equation weakly. So it's a weak formulation of this equation. And then we need some integrability properties, so all things are well defined, and this is to make the stochastic integral well defined. And here it would be, of course, enough to have p equal to 1, yeah, because if p equal to 1, it's enough because that's bounded. And this integral is well defined. But in general, we can prove for higher p, so we took this in the definition. Okay, so here's the first theorem. So under hypothesis 1, which is exactly this kind of psi, or we can also take the fast diffusion case, and under this condition of C infinity, there exists a solution. And now I would like, the proof we do here is different from the one that I mentioned before, so this minty trick and stuff like that doesn't come in, so we do a completely different proof. And this is a second way of solving these monotone equations, and you'll find that in the deterministic case, you find this way of solving this equation in all books. This is using the Yoshida approximation, and I would like to explain a little bit how to do that. So for every x in L4, this is the price we pay. We cannot start in every point in H minus 1, but exists a unique solution to our weak SPDE, weak in the sense of analysis, so we have to take test function, analytically strong, of course, probabilistically strong, so it's really a function of Brownian motion, the solution. Then for any such initial datum, there exists a unique solution, and if the initial condition is non-negative, also the solution is non-negative. It's very important, because if you start with a distribution of little sand pieces, with the distribution, and you would like to have a solution that is again describing a distribution of these little guys. It should be positive also later, otherwise it's not a distribution, it's not of these little particles. So that's a very important property, but it follows again from the linear structure of the noise, so it's linear and excellent, that's very important for that. Okay, so it's positivity preserving non-dynamics. Okay, now let us, just very briefly I would like to indicate how one proves this with this other method. So the first thing one does, one takes, just think of the sine function. Or think of just this first part in the fast diffusion case, so just the square root part. So for the psi, forget about the psi tilde which I add. Okay, so with the sine function, so you can define an approximation in the following way. You take identity plus lambda psi 0. Then you can prove by maximum monotonicity this is an invertible map. You take the inverse and then you apply psi 0 again. So concretely, you can just calculate in the case of the sine function looks like this. So it is a very simple approximation of the sine function that everybody of you has probably used already once in your life. It's this one. So this is the sine function, and you just approximate this. That would be the approximation, and 1 over lambda, lambda is just stupid. Okay, and this piece is exactly the lambda. Lambda will go to 0, and there's definitely, you see the approximation of the sine as the Lipschitz function. But the bad point about this Lipschitz function is it stays, of course, monotone all the time, and the monotonicity constant will be always the same. But the Lipschitz constant goes up in the limit, because in the limit the limit cannot be a Lipschitz function. Okay, and this is called the nonlinear Yoshida approximation, which you can do for every maximal monotone graph. So even if the psi 0 is multi-valued, this will be already single-valued, this inverse. If you think about my explanation of maximal monotone, you see immediately that this must be single-valued. And it is a Lipschitz function. Okay, so that's just an example. So I replace in my equation now, basically the psi, the bad psi 0, let's say, by psi lambda, and psi lambda is exactly here the Yoshida approximation, times rho, because our sine function had a coefficient in front, it was just half of this gap there, and then I add my function psi tilde, this is a nice Lipschitz function outside 0, so I can do it, and I also would like to make the system more regular to make it not degenerate, so I add lambda out. Okay, it doesn't really matter. But otherwise, it's exactly the same equation as there. Okay, now I solve this regularized equation. Now these guys are Lipschitz function, that makes life much easier. And we proved in an earlier paper that this, of course, may be tight, but in such a situation, quite standard methods give you a solution. And you can imagine that this is true. By the way, this Yoshida approximation, of course, everybody knows we see in the Yoshida theorem, because in the linear case it's the same. But it can be done for maximal monotone function. Okay, so we proved that for a given lambda we have a solution which has continuous path in H, has this integrability property, and also it preserves non-negativity of the initial condition. Okay? So then one can try to prove that these solutions they form a Cauchy sequence. So let's just take two of the solution at the point lambda, mu, compute the norm in H, which is the H minus 1 norm, and then in order to get rid of a term which I don't like, I take e to the minus ct for large C, and then you can prove, I mean simply by Ito's formula, that you have such an estimate. So it's less than the maximum of lambda and mu, and then this term. So you see if lambda and mu goes to 0, this term will vanish, and there is another term here, but then by Berkeley-Davis-Gummy inequality, you have managed so to prove, so here's this, I mean probably everybody knows how to do that this eventually goes to 0 if you first take the sup over T and then expectation. So that means we have a convergence of our process in this space. So we have a solution, candidate for the solution, and then we have to prove, so it's different from the other. Then we only have weak convergence, if you remember, in the general proof we get weak convergence of the Karyakin approximation, but for the Yoshida approximations, one can prove actually, in a sense, strong convergence in L2, even with sup over time, in this situation, with the porous medium. Okay, and then one has to prove the limit is a solution. Yeah, there, of course, one has to work. Yep.
For the approximations, you don't use the variational framework to prove that.
No, it's just it's by pure. Well, in some sense one does, but not as much as I said before, because now here everything is Lipschitz, and it's just by bare hands you can prove this. So there's nothing which we use.
So you don't get the solution in a more regular space here. It's everything is dealing with H. You can't get V even for the approximating equations.
We don't worry about that. It's a different approach. Okay, because we only write down the weak solutions, then as Professor Kuhler already stressed, then part of the big machinery drops out. If you just look weak solutions, in the sense that you take in a product with a test function. Yeah. So then you don't have to talk about all this VV star business. And that is similar here. And it works particularly well in the porous media case. Okay, so that gives us solutions. Now let us come to the question of extinction. So let's look at the solution from the theorem I just said. So we have in both cases, in the fast diffusion case and the self-organized criticality case, we have solutions. And now the first thing is that I claim that if I look at the extinction time, the first time process is 0, which can be described like this, then it will not resurrect afterwards. So that means for later times, it stays extinct almost surely. And of course this, well, probably you will immediately suggest another method in a minute, but my argument is simply by proving this guy is a supermartingale. And then remember what Duke said, life goes down in the mean, and once you're dead, you stay dead, individually, without taking the expectation. Okay, and that's exactly what it is. So that's a so then if the super martingale gets to 0, then it stays 0. And I will show you the sketch of the proof later on, because I need it for the extinction result anyway. And this is true in all dimensions. But nobody tells us why is this not plus infinity. No? Some probability is plus infinity. And this I want to prove that at least with strict positive probability is not infinity. So now here comes the specialty about one-dimensional case. We know that d is equal to 1, h1 is embedded into a continuous bounded continuous function, so then dualizing we get that L1 is contained in h minus 1. L1 is contained in h minus 1. So that's in the, what I call the self-organized criticality case. So we should always have two cases in mind. One is Heaviside function type psi, so that's the SOC case. And then is the fast diffusion case, the SD case, where the psi is of square root type. There's always two cases. And in this case, I always assume d equal to 1, and in the d case, in this theory, take only d less than 3. We can do all dimensions, but just for simplicity. Okay, so we have a square root type psi, and then we have our condition from the theorem. Remember, I always assume if it's anything, but in d equals 3, it is bigger than 1 over 5. Great to make it. Okay, I know this is a continuous embedding, so this norm is bigger than this one up to a constant, so let's take the corresponding constant, so that means the largest one for this is true, and so that means if I take this infimum and take the infimum, it must be strictly positive, because this is continuously embedded. And I need exactly this guy. So just compare the norm, this is the bigger one, and I take the infimum. This exactly, if you look at the continuity constant of this embedding is 1 over this continuity constant, of the optimal one. And then I do the same here. So what I forgotten to write here, that the same thing I use here, you can already imagine, that under this condition, L alpha plus 1 is contained in H minus 1 by some embedding. So that's exactly what we need. And in this case, as I said, of course, you can just copy from the proofs about the deterministic porous media equation, and then I can sort of guess that this is, see that this is important for the self-organized criticality case, and there is exactly what we need on dimensions. Okay, so now I look at this equation, and just, in order to convince you it is not important that critical case is 0, we can just subtract any L4 function here, and then reduce it to the case equal to 0 by looking at the process xt minus xc. So really the physicists are happy with our results, so we really have a critical case of an arbitrary shape. It's just about shifting the whole equation. You always get back to the case when it's identically equal to 0. Of course you have to also shift in the stochastic term. Yeah? Okay, so I just once wanted to show you how the equation looks like. And then, so this is a critical case, and now we start on the right of the critical case. So that corresponds to starting with x which are positive, and then we have the result. But now later on I will again take this equal to 0 without loss of generality. And then remember we have this condition that you do not shift this all the way down to 0. So that means if I look at the sum of the two, this is always strictly positive. So that means this is exactly, I should really keep one here. So this gap here is exactly the row 0. And this will come explicitly into the estimates, which is sort of understandable if you think, I mean, the more concave it is, the better the extinction results will be. So it is very concave, so it's Heaviside type, and it depends how large it is, even better. Yeah? And you will see that the estimates depend on the size of this guy. And here's the estimate. So the probability, now this is extinction at time xc, so now if this is 0, it's our old extinction time. So this is not dying, but going to the critical case, yeah, and we subtract, so it's dying. Okay, so then the probability that is less than the time t is quite big. So if t goes to infinity, we have some chance that this is really positive. So that means, because you see, because it could be that this is a very big number, yeah, and then you just prove that this probability is not negative. We knew this from the very beginning. Yeah? It should be big. So therefore, we have to make sure that this is less than 1, and that's exactly the condition for that. Because this integral is just it's 1 over c infinity, so it comes up in the denominator here. So that's exactly what you need in order to make this guy, at least for large t, it should be strictly positive. Okay. So now you might wonder, why don't you do this integral? Why don't you calculate it? Of course you can calculate it explicitly, but I would also like to include the case c infinity equal to 0. Yeah? Because then this is just t, yeah? You divide by t. Okay, so then we take the solution, forget about the shift now. So in particular, if we start close enough to the critical case, and our case close enough to 0, then you see immediately from here, if you have t to infinity, that is still positive, and you will get really the probability that this is finite is strictly positive. So if we can prove this estimate, we're done. And now I'm going to show you how to prove this estimate. So first, but before I do that, I do the FD case. This was the self-organized criticality case. Now the FD case equation is the same as we saw before, and we have the same kind of estimate, but only where the alpha comes in. And here the gamma alpha, this is this 1 over the continuity constant of the embedding of L alpha plus 1 into H minus 1. And in the other, the gamma, you see the gamma here? That's exactly the 1 over the continuity constant of L1 being embedded to H minus 1. So that the gamma comes in. Now this is a physical problem, so you would expect that there is not a mathematical constant inside the estimate. Yeah? Because this is mathematical, this embedding. I told a physicist and he didn't agree with me, maybe it's not mathematical because it's an embedding, a symbol of embedding, so energy comes in, so maybe there's even a physical interpretation for this constant, but I don't really know it. Maybe I understand roughly what it means. And the rho tilde, as I told you, that's the height, so that comes into the estimate. And we have the same in the FD case, so the rho, which is so we multiply the square, this root-like function with the rho, and this rho comes into the number. And also how diffusive it is, so how its alpha is closer to 0, so that means you can also see what happens to this probability. And again, so we have to make sure this is less than 1, so this is the kind of estimate, what you need in order to get that. So this is strictly positive for large t. So this less than 1 for large t. Okay, now let's look when the noise is 0, so that's why I chose this funny formulation without calculating its integral. Now we can put this equal to 0. Okay, then this is 1, so this is, you just divide this by 1 over t, and then of course you can calculate an estimate for the extinction time, so it is less than this quantity. And in the FD case the same, so then you get estimates for the corresponding times. Okay, now let's explain the idea of the proof. Yeah? It's not difficult. You just have to believe me that my calculations are correct, but I can sort of be checked with many times. So now this looks complicated, but now look, I'm going to take my solution, We know there's an eta formula, remember, for the H norm square, the pivot space norm square, we have an eta formula. So it's completely rigorous to do eta formula here. Now you can protest, you're not really in your framework, you only find weak solutions. But you can easily put it in the framework. Yeah? So there are several possibilities how to choose this V, in fact. So believe me, one can put it in, just skip this part. So there's a rigorous eta formula for the norm square. And then I just take a function of the norm squared, which, my aim is to get rid of the square. So what I do is I take such an approximation, take the square root of this guy, but I want to do it in a smooth way, so I add an epsilon. So now this is a nice and smooth function. So I apply eta formula to this real value semi-martingale composed with this phi epsilon. Because since it satisfies eta formula, this is a semi-martingale real value one, so I can just use eta's formula. And I've used it, forget about the first inequality, I've used it exactly in the lower part. Okay? So you see that is phi epsilon of my solution, and I use eta formula not from 0 to t, but from r to t. So this is the same, basically, so it's the same as the initial condition plus something. Okay? So the something you immediately recognize is the stochastic part. This is the remains of the eta part, which I called Z in my Z norm, so Hilbert-Schmidt norm Z squared, because there's more parts, but they have signs and they cancel out. They have minus signs, and I've left them out on the left-hand side. This is the nonlinear part. Remember that was the part x, ax in our eta formula, and I put this to the left-hand side of the equation. Now you might say here should really be Laplacian upside. But remember, I take the formula in H minus 1, so an H minus inner product appears between x and Laplace psi. But it's an H minus inner product, it drops out the Laplace term. You find a minus sign, but it goes on the right-hand side, I put it on the left, I get a plus. So that's exactly what comes out from eta's formula. It's really elementary. Okay, so then I do the following, I look at this guy. Now remember, psi is basically the sine function, plus a little bit. But the sine function, if you put it here, makes this just the L1 norm of x. You already know it's positive. I start with the positive initial condition. So we can even say this is, the sine function is 1. Yeah? So that's really not there. So that really what comes out is the L1 norm. Yeah? Because sine function, and this is positive, so this is 1. Yeah? Psi is basically the sine function. There's a little bit left to it, so therefore I don't get that this is the same as this, but it's bigger because I add this psi tilde, and the psi tilde I can estimate with the rho tilde. This is not rho tilde, with the rho tilde. I can estimate from below with the rho tilde. So you can just believe me, that's the right estimate from below. So then this guy is still there, yeah. And I have integral, and then this is just the L1 norm of x, because psi is basically the sine function. So we get this estimate. Now I put this in red, because in order to prove that I get the semi-martingale, you already see almost from here, sorry, the super-martingale, I will drop this term on the left. It's a positive term, and I will just drop it. But for the extinction result in one dimension, I need this term badly to get my estimate. Okay, so now let's remember that this thing by eta's formula is less than this thing. So next step is I estimate this guy now from below. Remember, this is bigger than the H minus 1 norm divided by multiplied by gamma. So I estimate this guy times rho, but from below by this times gamma. This I can only do in one dimension. But if I'm in higher dimension, I drop this term. It's not big. Okay? So let us just record in one dimension. I keep this term and I have this gamma. And there the gamma comes in. I used it very heavily. The reason why I have to do that is, you see, here's L1 and here's H minus 1, so I cannot really compare what is going on. But now I have H minus 1 and H minus 1 upstairs and downstairs. And now this term does something very nice in the limit, because now I take epsilon to 0. So we know this drops up the square. Remember, the phi epsilon was basically the square root. So I get this guy here. Here I get this guy, and what happens here, the epsilon goes to 0, I get exactly the same as in the numerator. So this cancels out. But you have to be careful, it only cancels out if it's not 0. Because if it was 0 in the first place, it will be 0 in the limit. So what comes out is exactly the indicator function where this is bigger than 0. If it is 0, it is 0 here all the time for every epsilon. In the limit, if it's not 0, this is 1. So I get exactly this guy. And this will give me the extinction, this term. Okay, on the right-hand side, you take epsilon to 0. You see this just converges. You see it's a 1/2. This goes to xs norm, and here's a norm squared. 1 cancels, you get this. And the same you get here if you calculate this guy, you get exactly this. It's not so important. This is just a martingale t, so this will not cause any big problem. Now I would like to get rid of this term. Yeah, so I just use the usual Grunwald trick. So I multiply e to the minus c infinity t, use Ito's product rule, and I get this guy. So this kind of inequality. So that's exactly my aim. And remember, in higher dimensions, I drop this. Only in one dimension I'm used to. So now from here it is completely clear. In all dimensions, I drop this, that this is a super martingale. You see that? Because you take expectation, the condition expectation with respect to fr, okay, then this survives. And here take condition expectation with respect to fr, since you integrate after time r, by its independent, so it's 0. So follows immediately this is a super martingale. So the above concept we can drop the non-negative red term starting from inequality 14 already, that's what I said. So hence 15 without the red term implies that for all dimensions, this is an FT super martingale for the, now doing the SOC case, I don't do the FT case, just the first case. Yeah, because I used that this psi is just the sine function, and then this becomes L1. Okay, so I know it's a super martingale, so I proved the previous proposition, if it's dead, you stay dead. Now I would like to prove extinction. Okay? So furthermore, since rho tilde is strictly positive, dropping the black term on the left, this is a misprint. I drop this one. Yeah? I can do it, it's positive. Inequality still holds. So forget about this term, and then I take r equal to 0. I look at the special case r equal to 0. Okay? So then I have just this term from 0 to t is less than, this is 1 for r equal to, this is just the initial condition x. You see that? Okay, and then we take expectation. We take expectation here, this is constant, x, this is exactly this, x minus 1 more. So I take expectation of this, and the expectation of this, of course, is 0, because it's a martingale in t. Yeah? So let's go. So I have the expectation of this is less or equal to x minus 1, r is 0. Okay? So that's the thing. So this I take to the other side, I put it there. So I have this is less than this. Now I look at this sharply, and then if you take s equal to t, I make this smaller. So I can take this out. So I get p t0 bigger than t is less than this, divide by this. And that's exactly how I estimate. Oops. It's exactly this. So what we learned from this, I mean, we got stuck for a long time, maybe we were just too stupid, but we really learned from this that such a term, that gives us extinction. So this is quite a hands-on approach. Meanwhile, we have a more sophisticated way of doing this with the help of Feng Yu 1. So we now have a more general technique to prove extinction for a more general class of SPDE. And that's a new paper that you can find on arXiv, and it will appear in Journal of London Mathematical Society soon. But to explain that technique is much more sophisticated. So this is, I think I like this proof because it's just Ito's formula. Yeah? But the other one doesn't give, well, it gives sort of better results in the following sense, where if you can, you see, what we have done right now, we have sort of used the competition between the two. Sort of, but only sort of. And this sort of was in my way because you remember there was a term on the right hand side I got rid of just by the Grunwald trick, e to the minus c infinity t. But otherwise I don't really use what is going on. But the method that Feng Yu suggested and then we worked out subsequently sort of takes into account the competition between this and this much better. As a result, here we only can prove extinction with positive probability, but as a result, you remember the Zhang model, there was a linear part here. So you have a much bigger part here, which is very good for us, this bigger part, because if you have a bigger part, somehow the extinction is better. Yeah, I told you before, if this comes in very big form, it's better extinction. So the competition is won by this drift. with respect to the diffusion, and we can prove this probability modular extinction. So his method takes better into account the competition between this and this than this hands-on method just using Ito's formula. So it's more sophisticated. We also use Ito formula in that paper all the time, but we use special, and you will be not surprised, Lyapunov functions, rather than just doing Ito formula from the norm square. Yeah? And we reduce it to a finite dimensional argument, and we use certain Lyapunov functions and so on. So just to give you some ideas. Okay, so to finish, let us look now in all dimensions at what we proved about asymptotic extinction. So far with extinction, really positive probability the thing is gone. At least in one dimension we can prove it, and also for the fast diffusion case and for the Zank model even 1. So now let's look what happens asymptotically. And so this is a paper with Viorel Barbu, which has meanwhile, I think it has appeared in Communication Mass Physics. And you see again we have the same initial conditions, so we have positive initial condition, and then we solve our equation. And now we asked, what about the L1 norm? Before we did estimates for the H minus 1 norm. Remember, we put the H minus 1 norm with 0 starting on a certain time. And we had a problem to compare the H minus 1 norm with the L1 norm. So why not work from the very beginning in the L1 norm? So that's the idea. Okay? That's not so easy because it's not a very smooth law, you can imagine. So it's not Ito formula and so on is out. Yeah? So you have to do other techniques. And what we basically prove is that the L1 norm, remember this is positive, this is really the L1 norm, is a nice semi-martingale. That's what we eventually prove. At least we can approximate it by nice semi-martingale. And then we can use a limit, but an elementary limit result, limiting result, you can find in the book of Shiryaev, Lipster Shiryaev, I think it is. This version you need, and you can prove there exists a limit. So that this always has a limit. So the L1 has a limit asymptotically, P almost surely. The thing that we cannot prove right away whether this limit is 0. That's what we want to prove. In the limit it vanishes in L1. But what we can prove is this thing. So I cannot explain the proof, it would be too long, but we can prove this thing. What is it? So we look at the Lebesgue measure, N is Lebesgue measure. We look at the Lebesgue measure of our underlying domain minus the points where the solution is already 0. So that's the bad set, yeah? Because we would like to prove extinction asymptotically. So we take our O and we subtract where it's already 0. So we have the remaining set, and we prove that this is integrable in T. So morally, if T becomes large, this must become small. At least it cannot be too big on sets of large measure. So this is already kind of an extinction result. Not the one we want, but at least it is a kind of extinction. And such kind of results, such kind of a result gives a lot of information. So this was a trick of Viorel, and he showed me that and said, well, okay, it's fine, and we can interpret it in a certain way, but what does it give analytically? And really, it has a lot of analytic consequences, but I would like to refer to the paper for that. It's technically not so easy to explain. Anyway, so we have this kind of thing, but that was not enough for us. We wanted to prove really that this is 0. We didn't succeed so far, but what we succeeded in is we proved the local L1 norm goes to 0. So if I now replace this, my whole domain, by a compact subset, then I can prove it converges to 0. So that means if you have a bounded domain and you look at the compact subset, then asymptotically there's nothing inside it. So we can only prove locally. And for that, the only technique we have is to use this transformed equation. And that's why I mentioned that this linear equation can be transformed into a deterministic equation with random coefficients. And you, of course, will imagine immediately the transformation. You take P to the Brownian motion in the noise times xt. I do not subtract the bracket. So some people don't like it because the normal transformation is subtract the bracket of this Brownian motion, but it doesn't help you. It makes things even more complicated in this case. For our purposes, so it's not good to subtract the bracket. Okay, and there are some technical problems, so we only proved the case, though I'm sure it is true. In the general case, we only proved it for finitely many modes. So our infinite sum, here in the noise, we assume to be a finite sum. And this is just in order to avoid discussions about interchange of limits and so on, but I think meanwhile I have conditions under which everything works also for n equal to infinity. Okay, so then I take this guy, and now I do this transformation. So be careful, this is not like in finite dimensions. You know this transformation probably from linear equation in non-dimensions, let's say. But you have to be careful, because now you would like to apply Ito's formula to prove that the y satisfies this equation. And remember, the eta is basically psi of x. Yeah? It's just this section in there, so it's really a single-valued equation. Yeah, so that's the psi of x. So here it's Heaviside function of x, and x is e to the mu t y. So what you have here is e to the mu t, Laplace e to the minus mu t y. So in a sense it's a porous media equation, so let me write this. So eta is basically a section of this, so basically it's the same as psi of x. It's a section in there. Now let me write it a bit more non-rigorously. This is the red line. I crossed the line. I should have crossed the line. So I write it here. Okay. So the equation is really this one. And in this form, it is much easier to remember. So it's e to the mu t, and then Laplace of psi. I just use this graphic psi of e to the minus mu t. Psi and t. And omega, but omega is fixed now. So this looks like a ground state transformation from physics. You multiply, you divide by a function, you do the operator, and you multiply by the function. But it's a nonlinear operator in the first place. This is a nonlinear operator. And the second, the function you scale by is time dependent. So it's not a ground state transformation in the classical sense, but it's a little bit similar. The bad point is that this transformation destroys the monotonicity property completely. So to solve this equation directly is really hard. We did it, but it is impossible to do it by monotonicity methods. And so how do you solve such an equation? You don't have much at your hands. So it can be solved. It's in this paper in JDE I mentioned, but you have to do really a hands-on approach. And the only thing, your tools is the maximum principle of the Laplacian. So that's the only thing we had. And we had to really reduce everything to that. And we can solve this equation for bounded initial conditions. Then it's really true. For every omega, there is a solution. Okay, but what is important here is just formally applying Ito's formula, you get this equation. And it's in a sense like a time-dependent ground state transformation. Now the other thing is, so for instance now if this is just some power, so now this is some power, you might think of, well, why don't I use the Leibniz rule to take out this thing? And this is the big difference if whether you take a function valued noise, you see Ek depends on psi. So here this depends on psi. So now if you use the Leibniz rule to take it out, you get a mess. The structure is completely destroyed. If you look at the noise, which is real valued, so or maybe RD values, so this doesn't depend on the spatial variable, then it doesn't make any problem because the Laplacian will not act on this guy. So if psi is just taking a power, then of course we can just take it off and basically will cancel most of whatever. There's of course a power left, but it doesn't. So it is let's say a big step from a real valued noise doing this kind of transformation to a noise that depends on the function. And now I said formally applying Ito's rule, but now I want to explain why I really have to have to say informally or non-rigorously or heuristically. You see, where do you want to apply Ito's rule, right? Well, this is a function value process. This is a function value process, so you have to find this should be in some kind of Banach algebra where you can apply Ito's product rule. So it's an infinite dimensional thing, and you multiply by two functions. But there's not a good way of thinking of that. So what we used here is also what Nick used in his paper about Ito formula for p-norms. What we have in mind, we evaluate, roughly speaking, this xi and this xi. This is non-rigorous, right? You cannot evaluate this xi. I mean, this guy is for almost all t only a function, and then can I evaluate xi? What does it mean? But the point is, at least heuristically, if a solution to a stochastic equation with this function value, you apply it upon psi. This is a linear map, if I can apply psi at all. It's a linear map. And then I told you, if you have a martingale on the linear map stays a martingale, real valued martingale. Semi-martingale stays a real semi-martingale. So you can apply Ito pointwise for fixed psi. And then if you fix psi, this is a just primary motion. But you have to make this rigorous. How do you make it rigorous? Well, you smear it with the test function and then just do the calculations. And you use very heavily the stochastic Fubini theorem to justify this. And you can find this in this communication mass physics. So finally we get this, and now I'm almost done. So using this, we now look at the asymptotic behavior of y. So if this gets extinct, xt gets extinct. So now we can use asymptotic extinction arguments for deterministic PDE. We didn't find a proper one that we can use, but using this property, we could do something, and what we get is the following. The y process really gets extinct in L1, so that's always true, but it's a y process. Now this is Brownian motion, so here's the thing is it also depends on psi, and this is oscillating like a Brownian motion, as I said. So we cannot conclude if this converges in L1, xt converges in L1. There's no way to do that. But by our results about the solution of this equation from the paper I mentioned in Journal of Differential Equations, it's really not so difficult, but if the noise, the mu tilde, I forgot to say that, is just basically mu tilde t is the bracket of this process. So now if this is positive, so that means if the eigenvalues are positive of the decay, so if this is strictly positive, this entire sum, there are of course examples, then we can prove what I already announced, we can prove this converges at least locally in L1. So locally this doesn't make a big difference if the noise is, if this mu tilde is strictly positive. So that comes out altogether. So we have asymptotic extinction in local L1 norm of the original process, and the scale process we have asymptotic extinction in general. So we have explicit estimates how this flows. So this is not so difficult. So it goes in fact exponentially and with full probability. So starting from time which is bigger than some time depending on omega, we have such an estimate, for instance. But this is more or less standard, so I don't want to go too much into this. And you see that the mu tilde comes in all the time in order to do the estimates. This is heavily based on this SPDE transforming into the PDE. Okay, and this we call this a scaled porous media equation, as I said, doing the scaling. It only works for linear multiplicative noise, and as I said, it does not fall into the class of monotonic equations, but we found some technique to solve it in this paper in Journal of Differential Equation. Now my last remark is the following, that this technique, this kind of transformation was exploited to its limit, I would say, again by my student Benjamin Guest, subsequently in his thesis. And the reason is, once you can transform such an equation into a deterministic equation, you can prove what is called the strong co-cycle property for the stochastic flow given by the stochastic partial differential equation. The strong co-cycle property is the same that probably you know when you study Markov processes, perfect additive functionals. There's always zero sets depend on time and you cannot get rid of them. And for the solution flow of the stochastic PDE, you have exactly the same problem. But if you can transform it into a deterministic PDE, you can argue omega once and you can control the zero sets. So he solved by this kind of transformation, transforming this equation and working with the deterministic equation, he could prove that stochastic porous media equation have random attractors. And that was an open problem in the case when there is not additive noise. For additive noise, we proved this several years ago, but for linear multiplicative noise, it was open, so many people tried their luck and failed, but now finally Benjamin, when he saw our transformation, of course this was one incentive to study this equation because I wanted to help him with his thesis, but when he saw this, he did a much better version of that. And so I would say now, you don't have to read this paper anymore, you should read Ben's paper, it's much better, but it's much harder to read. And then he uses a lot of regularity theory for deterministic quasi-linear equations, because this also gives you regularity results, right? Because if you look at the connection of the two solutions, so if you can prove regularity for the solution of the deterministic equation inside, follows also regularity here, because the eigenvectors are as smooth as you like. Okay, so he used then regularity theory about this classical Di Benedetto and other people, so he worked through this literature and can put very nice regularity results of solutions of stochastic porous media equation in the spatial variable by using this trick. And so eventually he was able to prove the existence of compact random attractors for the stochastic dynamical system determined by such a porous media equation. Okay, he did not do it for the Heaviside function, but for many other functions. But of course the technique is similar, and you have to be careful. It's technically not so easy, but now I think we have a very good tool to prove many things about solutions of, for instance, stochastic porous media equation. For instance, one other result that follows from this transformation, just to make you hopefully even more interested, is it's very difficult to prove localization for stochastic equations. So if you start in a compact set, then you'll wait a time, will you still be in a compact set, or will you be immediately all over the space? Okay? But you see, this property of being localized, if you want to prove it for x, it's enough to prove it for y. So you can again transform such localization question to the scale equation. And there is a new paper by Babu and myself on the Electronic Journal of Probability, where we prove localization for stochastic porous media equation if psi is a polynomial. So if you're interested, you can have a look. And this all depends on this scale, on this transformation. So I think now I've tortured you enough. Thank you very much.